Welcome back, students. Lesson 16, the video C. Let's do an example and learn how to do a hypothesis test, start to finish. Kim Shepard just gave us all the steps, so we're going to walk through the steps. You'll see that these aren't that bad. Found this fact on the internet. Educationportal.com had a couple of interesting facts. One fact was that cheating most often occurs in math and science courses. I believe that for sure. 75 to 98% of college students surveyed each year admit to cheating at some point during college. Certainly sounds like a confidence interval to me, right? It doesn't have a confidence level, but whenever you see that interval, that's what I'm thinking of. College students most likely to cheat are engineering and business majors. So all that being said, let's test for some evidence that more than 75% of students at a certain school cheat. We randomly, anonymously, confidentially collect data from 444 students. It turns out that 360 of them said that they have cheated in the past. So we're going to assume everybody's telling the truth here. There's no funny business with students lying or anything. Run the test, showing all steps. All right, so is there a number one there? Let's see. Number one, what's the first step? Running a hypothesis test. Read and reread that problem until we understand what the heck we're doing. We're starting with proportion problems for one sample, but as the course moves on, we're going to do two sample problems, and then we're going to do means, and one and two sample for means. So let's think about this. Determine if the variable is categorical or quantitative. Determine if we're working with proportions or means. One or two samples. All right, think of the data. The people administering the survey are asking students, do you cheat or don't you cheat? I would have a list of responses, yeses and nos, right? So the variable, let's jot a few notes down here. The variable in this problem is certainly categorical, right? Either you cheat or you don't. When we're working with categorical variables, this tells me we're working with proportions, right? And it's one sample. It's one sample of students from the college tested against the number. The number is 75%. So it's a proportion problem, and it's one sample. Just to clarify, like what would be a two-sample problem? Maybe we wanted to see if more males cheat than females, or maybe more females cheat than males, higher percentage. That'd be a two-sample problem. We'll get to that in the next lesson. Write down the hypotheses. All right, so here they come. H sub 0 for the null, H sub A for the alternative. I'm working with proportions, so the correct symbol is P. Let's put that in both spots. Always equals up in the null hypothesis. And what's the number we're testing? We're going to assume, to start, that 75% of the students at this school cheat. So P equals 0.75. And if you reread the problem, it said test for evidence that more, I hope it says that, yes. Let's test for evidence that more than 75% of students at a given school cheat. More than means greater than, so we put the greater than symbol there, and 0.75. Now one thing, I'm going to write in parentheses, this is sort of going on in my head, but it's not necessarily part of the hypotheses. Just to remind ourselves, the null is assumed true to start. Before we collect any data, the null is assumed true to start. We're looking for evidence that more than 75% cheats. I'll presume that 75% cheat. Now just one little technicality. Always put equals up here in the null. It's like a shortcut for undergraduate statistics courses. But really, what's implied here, we're sort of saying at most 75% cheat, and then I'm testing for more than 75. Okay, so if this seems like a bit of a mismatch or a very strange assumption that I'm assuming exactly 75% cheat. This is correct, put equals, and then we're going to cook up, you know, when we do the p-value and do the normal model, it'll be based on this assumption here. Okay, to summarize, always put equals up in the null hypothesis. All right, part 3 of any hypothesis test, we've got these hypotheses. We've got to check the conditions. There's 4 of them. Make sure you write these down. And number one, that variable is categorical. So that's, we're doing a proportion problem. Either you cheat or you don't. Number two, what kind of data? We hope for random samples, but we'll live with an unbiased sample. Now, if I read back to the question here, it says we randomly, anonymously, and confidentially collect the data. With those details, I can definitely assume here that the sample is at least unbiased, and it says random, so we've got that. All right, check that off of the list. Number three was the sample size requirement. So what is our sample size? If you look in the paragraph, we collected data from 444 students. So n equals 444. I don't know what college this is, but if I had 4,400 students, this would be 10% of 4,400. So as long as it's not, say, Cecil College, it's Towson or Hartford or UMBC or who knows what, there's more than 4,000 students at those schools. So we'll presume, right, we will presume this is less than 10% of the school's students. It probably is. I can't imagine. I mean, most colleges have this, at least 4,000 students going there. Just not Cecil. And what's the last condition? I need at least 10 successes and 10 failures in the data set, and we have those, right? How many students cheat? 360 admitted to cheating at some point in some form. So we have 360. Oh, you want to put quotes? I don't know if a success is cheating or not. All right. And let's see here. 444 students total, 360 of them said cheat. What's the difference? Is there 84 of them? So I'm just subtracting the 360 away. I guess we had 84 failures. And both of these numbers exceed 10. And so check everything off the list. I mean, it's really the first hypothesis test problem we're doing. How could the conditions not be met, right? Better variables categorical, samples random, sample size is less than 10% population, and we've got enough successes and failures. You're wondering why, number four, why do we check this? Is because normal model needs enough data to sort of kick in behind the scenes. So it seems a little weird, but that's the reason why we check that. Okay, so based on the sample, I'm flipping the page here. Number four, based on the collected sample data, convert the sample proportion to a test statistic. All right, remember, this is what we're testing here, but I'm going to make some space. Let me peek at the next slide here, do the p-value. All right, I'm going to put 4 and 5 side by side. So we'll put the p-value for 5 over there. This is the test statistic. All right, how do we calculate that? Now for this problem, you've got to think of the sample data. And the sample data can be summarized as p-hat. All right, and what did we have? Something out of 444, 360 out of 444. That's the percentage of cheaters. I guess that's about 81.1%. 0.811. All right. Before I run the test, ask yourself, viewer, are you convinced? Does that convince you that for the whole school, more than 75% are cheating? So think about it. We took one sample. There could be 10,000 students here. We just talked to 444. This is certainly more than 75%. Is it convincingly above? Can you conclude and feel confident in your conclusion that, yes, I'm convinced more than 75, or no, I'm not convinced? Sort of like to eyeball it, I don't know. It's like right there, isn't it? Run the test. That's why we run the test. Test statistic. Formula looks like this. Z equals, let's see here. I'll do the letters one more time. It's p hat minus p sub 0 all over big square root p0, 1 minus p0 over n. All right. Oh, where do you think? Here? Down here. Your p hat value is the sample value. It's the 0.811. I'm subtracting off, that's the hypothesized value. Remember, we're testing for greater than 0.75 or 75%. So that goes there. Down in the bottom, be careful. This will be 0.75. This will be 1 minus 0.75. And so I painted myself into a little bit of a corner here, but I got enough space. This, and how many students total? The n is 444. Yep. All right, so this is the calculation for the problem. If you're doing this on a calculator, I would get the answer to the top first and then sort of do like an answer divided by the square root. To do this in one step on, say, a TI calculator, you need some parentheses up top and some parentheses down below. Okay. We're trusting that at this point in the semester you can do these calculations, and so the test statistic equals about 2.97. It's a z-score, students. A z-score. You know what's a big z-score and what's an unusual z-score versus what's not unusual. And so up at the top, let me just sort of point an arrow here to this 0.881, and basically this is saying that our p hat is 2.97 standard deviations above 75%. It's fairly unusual, and in fact, it's like right on the border of, we said rare for 3, right? It's rare to have 3 standard deviations. So I think, like, my spidey sense is telling me that this is evidence. This is telling me that there is evidence more than 3/4 of the whole population are cheaters. Let's get the p-value. If I flip to number 5 here, test statistic first, p-value second. We don't want to get in the habit of making our decisions to reject or fail to reject based on this, because we're going to change all the rules of the game in about 2 lessons. So always convert this to a probability, get the p-value. P-value over here. We're going to draw a standard normal model. This is a z-curve. We've converted to z. The mean of the z-curve is always equal to, right? What is this? Let's see. This is a normal model, 0, 1. Pop 0 in there, that's the mean. I'm going to shade. I'm going to put a line at my test statistic. So at 2.97, way up here in the tail, that's my z-score from the data that we collected. This is z equals 2.97. Okay? In almost all cases, you shade out to the tails. But just think, why am I shading out to the tails? What kind of test did I do? Greater than test. Looking for evidence that more than 3/4 are cheaters. So we're going to shade up. I'm going to shade up here. That shaded stuff is the p-value. Now you're working with normal models. How do you get that area? You can go to StatCrunch. Use the normal model calculator. You know that the mean is 0, standard deviation is 1, and you're shading from a z-score of 297 and up. At this point in the semester, no-brainer. Better be a no-brainer at this point in the semester. It's 0.0015. And by the way, this came from StatCrunch. I don't magically know the answer to that. I do need to use the calculator as well. And so using StatCrunch, we got that p-value. All right. So there's 2 steps left, right? Part 6, we sort of need to make a judgment call. Reject or fail to reject. And then write a concluding remark. The p-value diagram that Kim drew up at the end of the last video, that thing holds for every hypothesis test. It doesn't matter what kind of problem that we're doing. So basically, and you'll get more experience as you do more problems, but where does this fall on that p-value diagram? The answer is way to the left, right? We said anything below 0.01 is overwhelming evidence in favor of the alternative, and 0.0015 is definitely less than 0.01. So maybe make some space here. Right. Leave that most important number there, the p-value. Part 6, if the p-value is small, then you'll reject the null hypothesis in favor of the alternative. P-value equals 0.0015 is extremely small. Sometimes it's hard to compare decimals, but 0.0015 is much less than 0.01. This is like magnitude below. Very small. When the p-values are small, reject the null. Right? In fact, if you wanted to, like a clear cut, since that p-value is less than 0.01, the decision always, don't think, don't blink, we reject the null in favor of the alternative. Write a concluding remark. This is overwhelming evidence. Maybe I'll even say that. Maybe I'll say something like this. Based on our sample, there's overwhelming evidence. Based on our sample, there is overwhelming evidence. The overwhelming evidence is me looking at this p-value after I ran through the hypothesis test. There's overwhelming evidence that more than 75% of all students at this college are cheaters. Based on our sample data, there is overwhelming evidence that more than 75% of all students at this college are cheaters. Remember, we're doing inference. I'm interested in some characteristics about the whole college. I had this thought, let's test for evidence. More than 3/4 are cheaters. Inference means take a sample, right? Use that sample to make a decision about a population, and we just did it. Now, a couple of notes and then we'll wrap up. I did not just prove that 81.1% of the whole school is cheaters. That's just the sample proportion. If we took another sample, which we ain't going to do, we would certainly get a different value. But statistically speaking, there is overwhelming evidence. In fact, that word might come up. These data are what we would call statistically significant, right? The data made us change our minds statistically, and so here's what we can say. Think back one lesson. Could you support your results with something like perhaps a confidence interval? Like maybe you're interested in some plausible values, like, well, for the whole school, give me some plausible values for the proportion of all of them who are cheaters, right? I bet if you did that, the whole interval would be above 75%, because these tests and these intervals that we've been doing in the last one are sort of telling us the same thing. All right, so good work. Keep your chins up. We'll see you in class. Thanks for watching.